All right, so we're going to compare exponential, linear, and quadratic. So with exponential, our equation, we talked about a few different equations, but one of the equations we looked at was a equals p 1 plus r to the t. We also looked at y equals a times b to the x. So these look different, but remember this just means our starting amount. The b or the 1 plus r, that's just whatever we're multiplying by. And then we have a variable up in the exponent, which is what makes it exponential. All right, linear, our equation will be y equals mx plus b. For quadratic, we did have a couple different versions. We had vertex form, intercept form, or standard form. I'll write our vertex form because that's really the one we use the most. So x minus h squared plus k. All right, so with exponents, for exponential, our exponents will be a variable, x or t. For linear, we will have no exponents. And for quadratic, our exponent will always be a 2. Okay, the shape of our graph, exponential is going to be curved. Linear will be a straight line. And quadratics will be a parabola. Our rate of change, exponentials, we called it two different things. It can be variable or constant percent. But that just means we're going up by the same percent each time. So it is in a way constant, but it's not going to be going up by the same number like linear is. So linear is a true constant rate of change, which means we're going to be adding or subtracting the same number each time. With exponential, that is not the case since it's a constant percent. We are going up by the same percent, but that means that we're multiplying or dividing by the same number each time. So there is a pattern. But it's going to be different than linear, right? And with quadratic, this one is also called variable because it is not a constant rate of change. So quadratic equations, we want to look for repeating numbers. And sometimes you won't see exact repeating numbers, but in your table, you will see the numbers go from negative to positive and back to negative or the other way around. But we will see those numbers go up and back down instead of with exponential and linear where they always go up or always go down. There is no turning point. So some special features, that would be one of our special features for quadratic. It has a vertex, which is our turning point, which none of the others have. All right, for exponential, it has an asymptote. Remember, it gets closer and closer to some number, but never touches it. And linear has neither of those things. It is just a straight line that goes on forever. All right, so even, odd, or neither. So remember, even means we can flip it over the y-axis and it matches on top of itself. So it is possible for quadratics to be even. As if we just look at y equals x squared before it is moved around the graph. That would be symmetric around the y-axis. Linear equations would be odd. Our linear parent function would be odd when we have y equals x. It would look something like that. Odd means that we can turn it upside down, turn the entire graph upside down, and it looks the same. And exponential will always be neither. Because with exponential, no matter where it is, we won't be able to flip it across the y-axis because one side will have an asymptote and one side will have a curve. They're never going to match up. And we also can't turn it upside down and match it on top of itself. So exponential will always be neither. Linear and quadratic, it is possible for linear to be odd, it is possible for quadratic to be even, depending on the graph. All right, so our table, if we had an exponential graph and it started with 5 and 10, and we know this graph is exponential, that means our next number has to be 20. Because with exponential, it has to be multiplying by something. So 5, 10, 20, 40, 80. Right, with linear, if it started with 5, 10, and we know it's linear, that means that those are going up by 5s. So we'd have 15, 20, 25. And with quadratic, you might see something like that. 4, 10, 12, 10, 4. So we would see the numbers start to increase and then they would go back down. We would see those numbers start to repeat. And that alerts us that it will be quadratic. And that middle number, 312, that would be our vertex. All right, so on number 1, we're looking at 3 cities, Coolville, Awesomeburg, and Fancytown. Coolville is growing at a constant rate of 80 people per year. Awesomeburg is growing and then decays, and Fancytown is growing by multiplying the population by 3%. So when we see constant rate, that should alert us that that one is going to be linear. So Coolville is going to be this linear graph here. And then Awesomeburg grows and then decays. So that is our parabola. It goes up and then it comes back down. Anything that talks about growing and decaying, or if it goes up in the air and then comes back down, that's going to be a parabola. All right, and then we have Fancytown is growing by multiplying the population. So anytime it's multiplying, that's going to be exponential. So that's going to be this curved one here. All right, so we labeled each one. We want to know what are the differences between these cities. So Coolville is going to be linear. Awesomeburg is quadratic. And Fancytown is exponential. Right, which city grows the fastest at the beginning? So if we look at the beginning here, Awesomeburg is way higher than either of the other ones. It is increasing very quickly and is much higher than the other two, around 60, 80-ish years. It's going to be way higher. So at the beginning, Awesomeburg is definitely growing the fastest. But if we continue this to infinity, if we just keep mapping these 3 cities from now to eternity, Awesomeburg is not the highest because it goes back down. And so we're looking at Coolville and Fancytown. Coolville is definitely higher than Fancytown until right before 140 years. Fancytown surpasses it. And this is what's always going to happen with exponential. Exponential is always going to eventually pass every other type of equation. So Fancytown will be the largest over time. So if we keep going to infinity, because it is exponential, and exponential will always surpass every other type of equation. Okay, so on number 2, we're going to find the average rate of change of the 3 cities in the table from year 0 to year 3. So average rate of change, you can do this a couple ways. We can see what we're adding each year. And then find the average of that. So in this one, we added 100. And then we added 150. And then we added this one we added 225. Okay. So we can say 100 plus 150 plus 225. And we divide by 3 because we're finding the average. When you're doing average, you add up whatever you have and you divide by how many numbers you have. So in this case, the average was 158.3. You can also just use your slope formula because average rate of change is the same as slope. So for that, we would do y minus y over x minus x, so 3 minus 0. And in that case, you get 675 minus 200, which is 475. And 475 over 3 gives us the same answer. So you can do it either way. You can count them and divide by how many you have, or you can use your slope formula, y minus y over x minus x. You get the same answer. So what this is saying is on average, City A is adding 158 people per year. We are not adding the same amount each year. So we know this one is not linear. This one is actually going to be exponential because if we take 300 divided by 200, we get 1.5. So in this case, we multiplied by 1.5, and 300 times 1.5 is 450, and 450 times 1.5 is 675. So this one we are multiplying by the same. All right, so let's find the average rate of change for City B. So City B, we added 300, then we added 100, then we subtracted 100. So when we see something go up and come back down, that should be a big red flag that that's going to be quadratic. So again, you can find the average of those numbers, or you can use your slope formula. So with the average, we have 300 plus 100 minus 100 divided by 3, and we get 100 on average. We are adding 100 each year, even though we added more than that and less than that, it averages out to 100. Right? Or we can use our slope formula. We say y minus y over x minus x. And we get 300 over 3, which is still 100. All right. And then our last one, when we look at this one, we go up by 40, and then we go up by 40, and we go up by 40. So since this one is adding the same amount every year, this one is going to be linear. And you can find the average like we did here. You can use your slope formula like we did here. But when it's linear, your average rate of change is always the same. So in this case, we don't have to go through all that. We don't have to put it into any formula because it is on average adding 40 every single year because it is constant. That number is not going up and going down. It is always the same. So this one will just be 40.